Okay, next up is the limit comparison test. And the limit comparison test is used in similar cases where you're asked to find an integral, an improper integral, determine whether it converges or diverges, that we can't solve by hand. If the positive functions f and g are continuous on a to infinity, and if the limit as x approaches infinity of f of x over g of x equals L, which is some finite value between 0 and infinity, then in conclusion, the integral from a to infinity of f of x dx and the integral from a to infinity of g of x dx both converge or diverge. So this is going to be another tool that, unless you're told to use one or the other, you can choose to use either DCT or LCT in situations where one of these will work. And so it's good to be able to use either one. And then when you get down to it and you start practicing these, you can kind of find which one works best for you. The nice thing about LCT is that we don't have to worry about the inequality of the two functions, but we are going to also need a comparison function. It's kind of built into the name of the test. All right, so let's look at a couple examples. So example 5 says determine if the integral from 4 to infinity of 2 over x plus e to the x dx converges or diverges. Okay, so if you notice, this is the same function as in example 3. And we found that one converges, so we're hoping that this one also does. But let's use a different test. Let's use this LCT. So let's use the same function that we did in example 3. Let's take away that x term in the denominator and use 2 over e to the x. And so setting up this, this limit here, we're going to take our original function over our comp function and look at the limit as x approaches infinity of that. So keep change flip to simplify it, and it simplifies down to e to the x over x plus e to the x. Since we're just looking at a limit here, we're not looking at an integral, then we can look at the end behavior model, right? We're looking at end behavior on the right end. And so e to the x is going to control growth more than the linear term in the denominator will. And so we can simplify it just to e to the x over itself, which is 1. That is a finite value between 0 and infinity. And so we've met the condition to use LCT. So now we can go to our comp function, and just like in DCT, we still have to take the integral of our comp function. Or just like in DCT, in LCT, whatever this integral does, our original function is also going to do. Okay, that's the difference in our two comparison tests. We already did that integral back in example 3 and found that it converges. And so our conclusion is that our original function that they ask us to take the integral of also converges, this time by LCT instead of DCT. Okay, example 6 says determine if the integral from 1 to infinity of dx over 2 plus x squared converges or diverges using the limit comparison test. Okay, so in this one, if we simplify that function of 1 over 2 plus x squared and just get rid of that constant in the bottom so that we've got 1 over x squared, we've got something that's reasonably simpler that we can take the integral of. And so we set up our limit of our original function over the comp function, keep change flip. We're looking at that, again, the limit as x approaches infinity, so we can look at the end behavior model to simplify things even more. And this one also goes to 1, which again is a finite number. And so we've met the condition to use the LCT. So now the conclusion of the LCT says that the integral of your comp function is going to behave the same way as the integral of what you're asked about. And so let's find the integral, the improper integral of our comp function. And conveniently enough, this is a piece series, so we don't even have to go through the antiderivative process. we can recognize our p-value as 2, which is bigger than 1. And so we know any of those p-values bigger than 1 converge. And so again, that we don't want to be done here. We don't want to circle this and call it a day. We want to make sure that we answer the question that we were asked. So we weren't asked about 1 over x squared. We were asked about 1 over 2 plus x squared. So we want to make sure that we give this conclusion statement and that we give LCT the credit. All right, and then lastly, in example 7, it says determine if the integral from 1 to infinity of dx over 5 plus x cubed converges or diverges using the LCT. Okay, same idea as the last one. We've got a constant plus a polynomial, a monomial in the denominator. So let's get rid of that constant. And 1 over x cubed makes a nice comp function that we can integrate. But let's make sure we meet the condition of the LCT first. Okay, so set it up as a limit, keep change flip, use your EBM. Again, we get another finite number. Again, it doesn't have to be 1. All these came out to be 1, but if we have another coefficient, any finite number, any positive finite number is gonna meet that condition. We do that. So again, find the integral of our comp function. It's also a p-series, also has a p-value bigger than 1, so that one also converges. And again, make sure that you answer the original question and you give credit to LCT.